Welcome back to CSC241, Introduction to Computer Architecture. The day and date is Wednesday, 22nd, 22 October 2025. And we are taking up our review of concepts and methods in Module 4, which has to do with digital components, the hardware digital components, the physical side of digital components. So we're actually getting into the chips and the stuff that goes on to motherboards and circuit boards and um, processors, memory modules, all the stuff that make devices, computerized devices, connected devices, Internet of Things, high tech, mobile data centers, servers, all of it, right? Anything that's digital. The focus of this module has to do with the physical hardware. And one of the things that I want to stress is that all of this is a semiconductor. Much of this, well, so there's a mix of conductors and semiconductors. The conductors for the wires and they're called traces on circuit boards. They're like flat wires. And as you look at physical chips and circuit boards, can everybody see this image here?
Yeah.
Okay, so those would be the conductors, the metal, and so the equivalent of pins or wires, yeah? Pins or wires. And the board itself that we imprint, so you'll hear a lot about imprinting or tracing. There's a chemical and a physical process to overlay these flat wires on the board itself has to provide separation between the wires, or it would all just be one giant shock effect. There wouldn't be anything productive. Everything would short out, right? Remember that you have to have ground. Everybody knows what I mean by ground, yeah? So you have to have a proper ground for things to work correctly physically. And can everybody see this screen?
Yeah.
Let's see if we can get a better view of this. So you have some elements in the table of periodic elements. And oh, come on. Yeah, it doesn't have that other image. So this is a view of the table of periodic elements, and when you look at the traces on the circuit board, that has to do with conductors or metals. The board itself has to insulate the differences between those. So it has to serve as the insulation around an electric wire. That would be the non-metals. And what's most important about digital components is that they're critically dependent on a group of elements on the periodic chart called semiconductors or semi-metals, right? Semiconductors. And so if you want to consider what digital components do, how many of you have washing machines. Have we talked about the washing machine phenomenon?
No, I don't think so.
This is the inside of a dishwasher. Can you see this?
Yeah.
Okay. Have any of you ever been camping?
Yeah, I have.
Okay. Have you ever used a garden hose to do your dishes?
Yeah.
Yeah, it's kind of like all or nothing, isn't it? You turn on a garden hose, there's this gush of water. It's a big flow of water. It's a lot of water, and it's hard to kind of work with, but you have to be selective about how you use that garden hose, right? In other words, you can't just have it on. Well, you can have it all on all the time, but that's not the most efficient use of water, is it? And it doesn't always work its best with cleaning the dishes. Um, True or false, you use less water with a dishwasher like this than you do if a human being washes the same set of dishes. True or false?
False.
Let me repeat the question. True or false? If you use a sink with a dish drain and you wash the same set of dishes by hand, you use more water than you would if you used a commercial, like a dishwasher appliance. True or false?
I would assume you use less water washing it on hand, because you could decide how much water to use.
Actually, the truth is you use a significant amount of water less with a dishwasher. Even if you do it by hand, the dishwasher recycles the water. So there are more. Now, dishwashers have come a long way. But the point is that dishwashers are more efficient with the use of water because they control the flow of water in different directions and they control the strength of the spray, the pressure behind the water, and where it's, so the nature of the stream, the pressure behind it, the amount of the flow, and they recycle all those things. The point I'm trying to make is that the water semi-flows in a dishwasher. It's controlled and it's recycled. And so there's a semi-flow of water in a dishwasher. Um, if you want to control the direction and the amount used and how it's applied in the same manner, semiconductors allow the partial flow. I want just conceptually, I want you to understand what's behind this. Semiconductors aren't like metals. Metals just let the electrons go. It's like the garden hose. Is everybody hearing what I'm saying here?
Yeah.
Okay. So so essentially you have metals that just let the electrons go. The electrons are free to move, and electrons don't like other electrons, so they move around quite a bit. The flow in metals is you would consider unrestricted. The flow of electrons forming a current, a flow of electrons is called a current. The pressure behind the electrons is called the voltage. The pressure behind is called the voltage. And there's a lot of similarities between the flow of electrons and the flow of water. There are a lot of analogous or similar kinds of principles and concepts, right? And semiconductors are good for creating digital components that control the flow of electrons in a specific way, okay? In a specific direction for a given purpose, kind of like the dishwasher, all right? Now, I know that's a crude analogy, but I want to make sure that that sticks. Semiconductors, now, the most prominent semiconductor that you know of is called silicon, right? And silicon as an element is not the same as the Silicon Valley or silicon chips because it's actually a compound that's used with the element. So there's oxygen in the mix. So oxygen is a non-metal. It's not even a semiconductor, but when it's combined with silicon, then that material allows you to create very specific objects that allow for the partial flow of electrons, and the the substrate itself. So we talked about etching and traces. The silicon wafer is like a miniaturized version of the large board that you see here. And what's etched into the silicon material are these traces that, based on the physical pattern, create different logic gates. Here is one example from your addendum. Can everybody see this?
Yeah.
Okay. Let me update the attendance roster. So basically, your grandparents knew how to build their own radio, and they actually used crystals, as in like rock crystals, a mineral that you can mine, and they would use a rock crystal and they would have tubes and transistors, okay? The first thing that appeared was a tube. It was a vacuum tube. And essentially, a vacuum tube was a physical way of organizing the material so that you'd have some very basic pieces. And depending on how the electrons flowed, you'd have the equivalent of an AND gate, an OR gate. Has anyone ever heard of resistors? Have you ever heard of the term resistor?
No, I don't think. No.
Okay. So resistors are like brakes or stops. They restrict or reduce the flow of electricity. And so resistors are a type of transistor. So when we talk about transistors, transistors were an advance. It was an innovation that let us step behind vacuum tubes. So when we talk about the history of electronics, the first computers were not made with transistors. The first computers were actually made out of vacuum tubes. Okay. And each one of these vacuum tubes was like, it embedded several logic gates. And this computer, one of the first computers that was ever built, was built with vacuum tubes. And let me tell you, your smartphone has more computing capacity than this computer. This computer took up an entire building, not a room, an entire building, and it required huge amounts of electricity, and it had all of the prowess of a graphing calculator, maybe not even that much. And that's an oversimplification, but essentially, vacuum tubes allowed for the material realization of the world's first computer. And it was called, well, ENIAC or ENIAC was one of the first computers, and it was made out of vacuum tubes, right? And it was massive, and it was hot, and it required all sorts of ventilation and cooling. And did I mention it had all of the strength of like a graphing calculator? Took up a whole building. So then transistors became a much smaller. So here's a picture of the physical. You have the pins or the wires, and then this piece right here is the actual, it's the equivalent of a tube. And now you don't have huge power requirements, and you don't have uh, cooling issues, and you don't take up so much space, right? And the first radios back in the 1930s, so we're talking about 100 years ago, had tubes. But by the time we had transistors, your grandparents were able to build their own handheld AM radio with a rock crystal, and the rock crystal had something to do with frequencies. Okay, so it had the crystal, um, the type of crystal meant that you could work with certain frequencies. And so we talked about switches before. Everybody remember the switch in the wiring diagram on the previous
Yeah.
study guide, right? So you have the switch is like a valve, okay? You talk about valves in a tube, a vacuum tube, switches in a transistor. Those allow you to control the flow of electrons, right? The collector is on the other side of the small cap to receive the electrons. So it's basically explaining that the emitter is what generates the flow of the electrons. The collector is what receives them on the other side. But then there's this other component in the middle that controls the flow on or off like a switch. And it's really important that you understand some essentials about the physical materials and that a proper electric ground is required. One of the things I want you to know is that 30% of hardware failures, computer hardware failures, electronic failures, mobile device, 30% of failures of computer hardware can be traced back to an issue with the electrical ground. How many of you are familiar with surge protectors?
Yeah.
Okay, so you know what a surge protector is. And the simple truth is a surge protector will protect against surges, meaning excess, too much voltage. So when the electrical supply exceeds the standard voltage that's supposed to be there, this basically protects your equipment. And some of these are sold, they're more expensive, but they have a built-in guarantee. When you buy the surge protector, if you buy a name brand surge protector, what happens is that you can replace damaged electronic equipment by filing a claim. So the surge protector is supposed to cut off the excess electricity. And it's supposed to cut off the electricity. And if it doesn't do its job, then you get to file a claim and replace up to $10,000 or $50,000 of connected equipment that are supposed to be protected by the surge protector. But there's only one problem with that. There's a couple of problems with that whole concept. The first thing is surges are only half the problem. It's the lower voltage that can also damage electronics and equipment. Those are called brownouts. So instead of blackouts, which is a total loss of electric, a brownout is sort of like, I got part of I got part of the current and the voltage. I don't have all of it. If you have lower current and lower voltage, the surge protector doesn't do one thing to protect you from that problem. The surge protector only protects you from excess or surplus, like when there's a lightning strike or when the generators at WAPA kick back on and there's a sudden burst of electricity. That's what a surge protector helps you do. But there's one Achilles heel of this surge protector that's a gotcha. And I want you to remember this. If you lose equipment and you file the claim, the first thing they're going to do is they're going to say, okay, we'll replace your $2,000 flat screen TV and your home entertainment system. Oh, and your computer system, well, that's another $2,000. Okay, so we'll replace the $5,000 of equipment. We just need to send an electrician to your house. Excuse me? Your house? Why would you do that? The first thing the electrician is going to do, a licensed bonded electrician who works for them, they're gonna test to see that you have a proper ground connected to the electric outlet. Why would that matter? It just so happens that when you have excess electricity, this thing cuts off the excess, but where does it go? You have extra electricity. What do you do with it? The surge protector is capable of protecting your equipment if and only if there's a proper ground. The excess current is redirected and it's taken out by the ground. And what happens if you don't have a proper ground with your electrical outlet? See in the fine print on that insurance policy that all right, so you can buy a surge protector at Super Dollar and you can just get a basic one and it doesn't have an insurance policy with it. And it'll probably cost you $5, $7. Okay, everybody with me? $10 maybe. But
Okay.
then,
Yeah.
but then you go to an electronics store, and the electronics salesman, the salesman in the electronics store goes, "Oh, you need one of these. These top quality surge protector, right? It's going to protect your USB devices and your home appliances, and it comes with an insurance, right? So you get the documentation out of the box when you unpack this thing, and if you read the fine print, it says, "Hey, we don't replace anything if you don't have a properly grounded outlet." 30% of all hardware, computer electronic, and computer digital components fail. Ultimately, 30%, 3 out of 10 failures can be traced back to what? An improper ground. You see this whole idea of controlling the flow of a dishwasher, right? Let's go back to the dishwasher analogy. See, if you can't control, we said that it recycles water. Well, that's because there's a drain, and there's a drain with a control that cuts on or off. The drain is open, the drain is closed. Everybody with me? Right? So, what happens with the controls if the ground isn't there? That's just like saying that the drain is always open. So you're not recycling anything, you're not controlling it. You might as well take out the garden hose again, right? Does everybody hear what I'm saying? Now, I know that's an oversimplification, but I want you to understand that dynamic. And if you have a link here, this is the study guide addendum, and in the study guide, there are going to be links. And you need to spend quality time on those websites. I think I already opened that one, right? Yeah, I did. Okay, so we're back to this one. And this is the same website, but if you look further down, it has more information. Here's some other examples of other transistors, right? So you can see there's some plastic that encases the components. And here, so in the switch is inside, it's embedded inside, but this is like a plastic in a case around it. It's molded, and this one has a metal one that's molded. And it's essentially, this is really good information. Now, there are YouTube videos. Watch the YouTube videos. Why? Um, it's in the references folder, which means you got to know this information. Okay? I'm just saying. There's all sorts of module for the assessment in this module. There are all sorts of assessment items. Oh, and while we're on the topic of assessment items, how many of you remember from our last session, there's a quiz that's due today, and I wanted to give you 48 hours. There was a little bit of a delay putting it out there over the weekend, after our last class on Friday. So because it was put out there a little later over the weekend, the deadline is 11:59 p.m. today, and only some of you have finished this. Remember, if you don't log your first attempt, then you don't get to reconcile anything. You don't get a second chance to improve your score and all that, right? So the other thing I'd tell you is that beginning with this module, when we go when we're finished, I will not be taking up class time for item analysis. So beginning with, you sort of graduated here. We went through a couple of sessions where we reviewed the items on the assessment that posed the greatest challenge. And what's going to happen instead is that after you've finished your first attempt of this module assessment, I'm going to post the reconciliation and a pre-recorded segment where I review. It's not in class, but I still review the items that pose the greatest challenge. We just don't take up class time for it. It'll be a link that's embedded in the reconciliation announcement. Does everybody understand what I just said?
Yeah.
Okay. Now, remember, if it's in the references folder, you got to know it cold, memorize it, learn it, study it. Don't just glance over it, engage it. And this is the part of the course where we lose a lot of quality of work from some students because they're in the habit of just like doing the fast and easy. You really need to spend quality time. You're going to have to, from this point on, you'll need to spend more quality time on the references. I need to hit the pause button. I'll be right back. I need 60 seconds. Please hold. Okay, we're back. Can everybody see the screen?
Yes.
Yes.
Okay. Thank you for that brief pause. I think we're good. So you can, all right, so you can see this. The You're going to see other YouTube videos in the mix, and it'll be talking about so this builds on the material the concepts and methods that we covered in modules 2 and 3, especially when we start getting into things like XORs and XNORs, the NANDs in particular. NANDs are used in a variety of really creative ways to produce the different logic gates. In fact, NANDs and NORs can be used in the physical world to build the basic and or and not. Now that seems kind of like circular logic. Which came first, the chicken or the egg, right? So in order to build a NAND, you have to have a not and an and. Well, physically, if you have a physical digital component that behaves like a NAND, then you use those in combination to create and or and not in the physical world. And that's a little bit of a leap or a loop in logic, more precisely. And that's something I need you to be aware of when you see references to uh, the hardware components that go in there and you're looking at it and it shows a NAND logic gate. It's the digital component that's the physical equivalent of a NAND that's doing that. Um, and so NAND is used quite a bit, it turns out, in non-volatile memory. This is something that this is another reference here that talks about the non-volatile memory. Please tell me, some of you have heard of solid state hard drives, right? SSDs? Yeah?
Yeah.
Okay, so solid state hard drives, the digital information, the data, the ones and zeros that are stored in disks, when the power goes off, the data remains. The ones and zeros don't go away. But there's this other type of memory, active memory, that the CPU, the processor works with, and it's a temporary workspace for the CPU to store intermediate results when data is being processed. So when the digital information or data is being retrieved or it's being received through input and output or from a disk, it's stored temporarily in random access memory. Now that's much higher speed memory. And again, it's like the workspace for a CPU. But when the power goes off, when you power off a computer or a mobile device and you wait just a few seconds, the ones and zeros, the digital information, the data doesn't last. That's called that's called volatile memory, right? There's also some memory registers that are embedded in the processor to help speed up the processor. These are it's called cache memory, or it's uh it's processor cache. And there's level 1 and level 2. You'll learn more about that soon. But basically, there are smaller stores of volatile memory that are on the chip itself, especially if the information is reused over and over again, like a certain constant. Let's say you're calculating the surface area of circles and the value of pi is used over and over and over again. Everybody knows what the value of pi is, right? Can anybody tell me, can you unmute your microphone and just rattle off a few of the numbers for the value of pi?
3.14.
3.14, thank you. Yeah. So if you use that over and over again, right, it doesn't make sense to store that on a disk where you have to read and write that through input and output that's slower. It doesn't even make sense to have the value of pi in RAM because once you're using it over and over again, you're just going to have that 3.1415927, blah, 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 whatever, how many characters of pi you want to take that out to. It's going to be in the local memory storage that's like the flash in the pan. This is even more volatile. So this is non-volatile memory on the hard disk. This is volatile memory that disappears in a few seconds. This is super fast, super volatile, disappears in the blink of an eye, microsecond or nanosecond, it's gone, right? On the CPU itself. And here's a fun fact. So, have you ever seen chip manufacturing facilities and the people in there look like they're wearing spacesuits? Yes, no,
Yeah.
maybe? Spacesuits. Okay. So, let's see, chip fabrication workers, sterile suits. So, most production facilities that we know of that produce goods, those are called factories. Yeah. In the electronic world, in the computer world, was special. Those are called fabrication facilities, chip fabrication facilities. You could call it a chip factory, but it's not like any other factory. See, in most factories, why is that? In most factories, the workers don't have to do this. Well, they might have protective gear to keep from being injured, strain, muscle strain, repetitive injury, that kind of thing, right? We're not talking about that. Here, in a fabrication facility, the chips are so small, the dust and hair impurities, when the silicon wafers are being produced, any dust or hair that gets in the mix makes for a less pure material. Now, here's the part I want you to understand. Can everybody see this image here? Right here.
Yeah.
Okay. So this is an Intel i7 processor, yeah? And normally it operates at 2.4 gigahertz, but in burst mode, it can operate for short periods of time up to 4.7 gigahertz. That's the number of computational cycles per second. It has to do with the speed of a processor. Is everybody with me?
Yeah.
Okay, so this is the important part to understand. The same i7 that's less expensive that operates in mobile devices and can operate up to 1.6 gigahertz. And for short bursts, it'll go up to like 3 gigahertz. The only difference between that chip and this chip is the amount of impurities in the material. Well, what am I saying? Um, this business right here is incredibly significant. The more impurities in the silicon wafer, the slower the speed it must run because it generates too much heat. When the material that the chips are made of is more pure, fewer impurities, fewer dust particles, less dirt, less hair, just stuff floating in the air, right? When the chip material is very, very pure, you can run much, much higher speeds. Now, I want you to notice that this is something of a tangle because AMD rates their processors. You've heard of AMD and Intel, right? Everybody's heard of AMD and Intel?
Yeah.
Advanced Micro Devices versus Intel. Okay. So they have these chips, AMD chips, and they tend to run faster, but they also require more cooling. So you have to have better cooling components. You have to have a bigger fan, or you have to even have water-cooled CPU cooling components, right? And that's because the chip runs that much hotter. It runs reliably, it just runs hotter, and you have to deal with the heat. And so AMD typically requires more cooling than it typically requires more cooling than Intel processors. But that whole cooling thing is there because of the impurities. And that's something that we want you to understand about the physical materials and the manufacturing process, which occurs in a fabrication facility where people have to wear spacesuits, and it's not to stay safe, it's to keep the chips pure. Does everybody know what I'm talking about here?
Yes.
Now, does everybody remember the mux and the demux?
Yeah.
Okay. In chapter 3, did we have something called a DFF, a digital flip-flop in chapter 3? I'm just trying to remember if it was in the study guide. I don't think it was. Let's search here. Mux. Whoops. DFF. No results. Okay. That's what I thought. The mux and the demux allow you to select, and that's incredibly important. However, once you have some basic simple capacities, simple functions, you have the basis for innovation and revolution. Let's talk about the DFF, okay? So you have a mux and a demux, and I want you to remember that the mux allows you to switch the inputs, right? It allows you to switch inputs. And what we're going to do here, well, you know what? I think it might be better for me to just finish up with this materials part. Let's save that for the class on Friday. Remember, on Friday, we will not spend time in class to review the items on the Module 3 assessment that pose the greatest challenge. We're just going to post the reconciliation with a link. Everybody heard that, right?
Yeah.
Okay. So essentially, you have this materials interest, and it talks about the early components in the history of design and innovation. And there's this distinction between CMOS and TTL. One of the most important things to understand about the shift from using TTL components, those are the earlier components, to CMOS, and it's explained down in here about what that acronym means, is that the voltage and power requirements are greatly reduced. So the early materials required more power, just as tubes required lots of ventilation for the heat and ginormous amounts of electricity, right? as you start to innovate and shrink the size of the components, right? And we're using, so the raw material for the semiconductor wafer fabrication is called silica. And yes, there's many more links for many more. These are videos that show you about the silica. I'm not gonna go through that, but I want you to know you have to watch this and you have to learn what's in there. Okay? And they're very short videos. Here it talks about the different uses of different types of metal for the traces on the circuit boards: copper, aluminum, yes, gold. We used to use gold much more often. You can often melt down older circuit boards and retrieve silver and gold from those. Of course, there's other stuff that you don't want, so and some of it's toxic, so it's not that simple, but there is something to be said for salvage. Old telephones used to have a crazy amount of gold on the contacts for the wires inside an old-timey telephone, the kind that bolts onto the wall, that's got a cable you can't remove. So you have other semi-metals that are used for special case fabrications, in particular germanium and gallium arsenide. And so you've heard of arsenic, yeah? The rat poison. Well, arsenic compounds can be used to poison rats, but other arsenide compounds can be used to produce chips for special cases. Here it says something about 3D transistors.
Hello, I'm Mark Bohr, a senior fellow here at Intel. Most people know it.
Now, his name is Mark Bohr, but this is not a boring video. Okay? I'm just saying. Don't lose your sense of humor while you're doing all this, right? Let's see, where are we here? We're about to finish. So over time, the trend was to make things smaller and smaller and smaller. And that meant that you could store thousands, tens of thousands, hundreds of thousands. And so that gave rise to all kinds of abbreviations or acronyms. IC stands for integrated circuit. That's when you have a bunch of logic gates on one chip. So you have a bunch of logic gates on one chip. That's called an integrated circuit, or chip for short. And so that's where the term originates. Over time, the amount of voltage required dropped from 5 volts to like 2 or 1 volt. And that's because the components became very, very small, so you could put very, very much larger numbers of digital components on the same chip. A very large scale integrated chip is called a VLSI chip, okay? And it has all those terms at the website. Remember that the MUX allows for a switch, and that switch can be used in a really creative way to give us a digital component that it's called a flip-flop, a digital flip-flop, or a DFF. And one thing I want you to understand about the digital flip-flop, you've heard the term switch. Well, a switch is like a gate, and a gate without a latch is a gate that you can't control. Let's say that again. A switch, a physical switch, is kind of like a gate that's made out of metal, and you can close the gate and complete the circuit. The thing to understand about a gate is that every gate needs a latch, or it's not a gate at all. You can't really control the state. You can't maintain the state. That's the important thing to understand. You cannot maintain the state of the gate or the switch without control. And the DFF is used in combination. We'll take this up We'll take this up at the start of the next class. But the advent of the DAFF, the digital flip-flop, it allows us to create digital logic that has a sequence. It has a series of events where we do specific things in a specific order based on a clock. So there's a timing component and a sequence component that becomes possible, and that tips the scale. That's like a tipping point where electronic innovation took off like a rocket. It's one of the less appreciated but more profound developments. We'll take that up at the start of our next class. Does anyone have any comments, questions, or observations before we close today?
Could I speak with you to review something after class?
Yes. Anyone else?
I just wanted to know, I think I missed something in my last submission. If I could add it to my submission.
Yes, you can. And then resubmit.
Okay, thanks.
Yeah. Okay. We'll close, and until our next class, good luck with your first attempt at the Module 3 assessment. For those of you who have not completed the Module 3 assessment, you have until 11:59 p.m. today. Please be sure you get that done, and we'll see you on Friday. Until then, be safe. Take care.